Okay, so today we are factoring special cases. So in the past, what we've done is we've factored three-term expressions. We call this a trinomial, three terms, tricycle. So we've been factoring trinomials with using the area model and the diamond or X. And then we looked at situations where maybe one of the terms was missing or they were out of order and how to deal with that, factoring completely, like looking for a common number. And now we're going to look at a couple of special factoring patterns that will help save us a lot of time and energy once we know the pattern. It's like a shortcut. So here's your essential question. How do you identify and factor a perfect square trinomial? How do you identify and factor a difference of squares? So if you don't know what these are, it's fine. You can just indicate on your slide that you don't know. If you have any ideas though, this is your moment. I'll give you like 20 seconds to just jot down any like first thoughts about any of this. All right, I see some I'm not sure, I don't know, something to do with factoring. Not sure what a trinomial is. I don't know. Don't know, Chief. Thanks. I like that. I don't know. Okay. Most people are like, I'm just not sure what this is. And that's absolutely fine. That's absolutely fine. All right. So let's learn it. All right, so here's our first slide, and this is going to feel a little bit crunched because we've got 4 problems all in one slide, but it's going to give us a chance to do a little practice factoring. So I'm going to remind you of the process. This is not different than what we've done before, and we're going to do, area model. Let me set this up. Okay. And then remember, we get our first term and our last term, and we plug them in diagonally in our area model. We multiply them together. We multiply them together to find the top of the X. We use our middle term on the bottom of the X. And we need 2 numbers that multiply together to make 25x squared. But add together to make -10. Sorry, excuse me. All right. So 2 numbers that do that, -5x, x, oh my gosh, and -5x. And so those are going to go in our area model. And then we need our length and our width of our rectangle. And look at that. There's our factored form. So I'd like you to go ahead and work on the next 3. I'm going to give you like, let's go 5-6 minutes. I'd like you to get through at least 2 of these. If you don't get all 3 of the remaining ones, that's okay. If you're working on a separate sheet of paper, that's absolutely fine. Just go ahead and put your answers on the slide when you have found them, okay? All right, and I'm just monitoring your progress now. So keep in mind, I can tell who's participating and who's not. I see 5 people who have not put anything on their slide yet. So if you're doing this on separate paper, just make sure that you indicate to me what's going on, okay? I think we're having some technical difficulties from some people. So if your computer's freezing or something, I totally understand. Okay. And if you have a question you want to put in the chat privately, go ahead and do that. Okay. Okay, let's go a couple more minutes, 2 more minutes, everyone. I see some great work happening here from a lot of you, so that's good to see. Here we go. 1 more minute so that you can finish up the problem you're on. And if you don't get all of them, that's okay. This is just a review, and then we're going to start looking for a real pattern here. So if you finish them, you know, take a close look at your answers and see if you're seeing a pattern. And we'll check our answers on the second screen, on the next screen, excuse me. Okay, so about 30 more seconds. Okay. All right, so wrap it up. I'm going to go ahead and clear mine, and we're going to check our answers on the next screen. So here we go. Okay, so here are the original problems along with this factored form in blue. So I want you to take a look at each of these 4 problems and their solutions, and try to explain what similarities you notice. Like, what is this pattern? What pattern do you see here? And this is one of those things that I think everybody can see a pattern here. We're not thinking too far outside the box. Just like take a look at the numbers, the expressions that you see in each of the factors, and jot down a quick explanation of what you notice. Okay, so now look, if you're really not sure, look at the two factors. So by factors, I mean like in this first problem, x minus 5 is one of the factors and x minus 5 is the other factor. Now take a look at the two factors in the next one, x minus 3 and x minus 3. Now we have 2x plus 5 and 2x plus 5. Now we have 3x plus 2 and 3x plus 2. What seems to be true for every single one of these answers? All right, so if you thought something like, the two factors are the same as each other, you would be correct. They are the same as each other. In fact, um, they're so much alike each other that we could actually write them like this. When you have something multiplied by itself, you could write it like this. So if anyone feels like that is less to write and you'd rather write it like this, then by all means, do that. And I'm going to do that because this is sort of a detail about this special pattern that helps give it its name. So this special pattern that we're looking at here is called perfect square trinomial. Perfect square trinomial. Perfect square trinomials, let's talk through each of these terms here. Let's start with what does it mean to be a trinomial, just so we know what that means, all right? So trinomial means three numbers. So like tri is three, like tricycle has three wheels. Nomial, it means it's like related to number. So when I say trinomial, what I mean is three terms in an expression. So our first example here, like x squared, negative 10x, and 25, that's three terms. So therefore it's a trinomial. So when we're talking about a trinomial, we mean just an expression with three terms. And look, all of these have it. 1, 2, 3. 1, 2, 3. 1, 2, 3. So these are all trinomials. And we've factored trinomials before. But this pattern is what we call a perfect square trinomial. And the perfect square part of this name comes from that the two factors are identical. And the reason why is because when we're doing these factoring problems and we have this expression, this trinomial, what the original problem represents is the area of a rectangle. The area of a rectangle, actually, let me do this with the box turn tool. The area of the rectangle as a sum is the three terms in your trinomial. But the area of a rectangle as a product is the two factors. So like in x minus 5 times x minus 5, one of these represents the length and one of these represents the width of a rectangle. So let's say one edge is x minus 5 down here, like a length, and a width also x minus 5 over here. Well, if you have two sides of a rectangle, If the length and the width of a rectangle are equal to each other, that actually means that this rectangle is not just any old rectangle, it is a square. It's a perfect square because the lengths of the sides are the same. If we had a value for x, like say x was 8, and I plugged in an 8 to this expression, 8 minus 5 is 3, and then I plugged it in here, 8 minus 5 is 3, I would have a 3 by 3 square. So these trinomials factored in a way that the two factors, the length and the width of their rectangle, were actually equal, making them all squares. So a perfect square trinomial is a trinomial that factors with two equal factors. And there's a way to identify the pattern of the numbers here as well, and we'll look at that on a later slide. But just as a preliminary, just to point out to you, I want you to notice that, for example, in this problem, x squared, see we have x squared here, the square root of x squared, so the number times itself, which is x, and then we have 9 here, the square root of 9, which is 3, because 3 times 3 is 9. The x square root and the 3, that's the square root of 9, are the numbers in our factors, x and 3. Notice it here, x squared and 25. So the roots of those are x and 5. In this one, the square root of 4x squared is 2x, and the square root of 25 is 5. So 2x and 5 are in our factors. This is a consistent pattern for this particular special situation. Okay, and we'll look at in more detail how to really identify that pattern and how to use it. Okay, so I'm going to go ahead and clear here. All right, and now we're going to look for another type of pattern. So we've actually factored expressions like this before, and I want you to notice, first off, these are not trinomials anymore, so it's not the same thing. These are binomials. They have 2 terms, not 3 terms. And remember, in standard form of a quadratic expression, ax squared plus bx plus c. In these expressions, what's missing is the b term, the middle term. So if we don't have another way, if we don't know the pattern, then what we can do to factor this is start by rewriting it with the missing term included. So like, instead of just x squared minus 36, I have x squared plus 0x minus 36. And then what that does is it gives us a chance to use our factoring process that we've been working on. So set this thing up. Okay. So then, and we just follow the same process that we've been doing. So we have an x squared here. We have a negative 36 here. We multiply those together to get the top of our x. The 0x in the middle goes in the bottom of the x. And then we need 2 terms that multiply to be negative 36x squared, but add to be 0. And the combo that does that is 6x and negative 6x. So that completes our area model. And then finally, we get our edge lengths. Oops, just kidding. There we go. All right, so our factors are x minus 6 along one edge and x plus 6 along the other edge. Notice how these factors are not the same as each other. One is positive, one is negative. So let's go ahead and take a few minutes to complete the rest of them. If you start to see a pattern and you want to shorten your work by using the pattern, you can. But I'd like to see everyone factor the remaining 3, at least get as far as you can in the next 5 minutes, okay? So let's go ahead and get started. And remember, in each one of these, the middle term is missing. So the bottom of your x will be a 0, whether you rewrite the expression out or not. And if you have a question, feel free to private message me, okay? So remember, I just want you to keep very close attention to your signs of your numbers. Notice how the signs in my example here, 6x and negative 6x made our factors look like x minus 6 for one of them and x plus 6 for the other one. So these aren't identical. This is not a perfect square trinomial situation. So the two factors will not be the same, exactly the same as each other, okay? So just make sure you're being very careful with your details when you write down your factored answers. I see a lot of great work though. Excellent work, people. So many are looking so good right now. Okay, we're just going to go for about 2 more minutes. So I know some people are finishing up, but other people aren't quite there yet. So just do as much as you can in this time. And those of you who finished, sit tight for a minute. And then we'll check our answers on the next slide. Okay, so let's wrap it up. And remember, your end goal is to get those two factors. So you want to definitely write out your factors at the end of each one. Okay. All right, so I'm going to go ahead and clear my slide and move to the next one. So if you do need to go back to this, you can absolutely do that when it's student paced. Okay. All right, next slide. Here are your answers. So take a close look at the answers that we should have gotten on the previous slide. And if you made errors, that's okay at this point. If you made some errors here or there. What I want you to do now is concentrate on the pattern. So what do you notice from answer to answer? How do the factors relate to each other? What pattern do you see? And then if you want to think even further, how do the numbers in the factors relate to the original expression? Any insights there that you can come up with is going to be great. Okay. All right, so what I'm seeing from the class is responses like they are mostly identical, but one has a positive number and the other has a negative. They both use the same numbers, but they use different operators. Okay, yeah, plus or minus. I kind of see the pattern for each. One of them is negative, the other is positive. Yeah, yes, that makes sense. All right, so hopefully that was like the idea that you had looking at these, and that's absolutely right. So this is a special pattern as well. The two factors don't match each other exactly, but they're really close. But one is positive and one is negative. So these don't technically represent a square the way that the other ones did. Because if you could imagine a rectangle that had like, say one side was x plus 6 and one side was x minus 6. They're not matching. If I had a value of x, like say I knew x was 10, then this side of the rectangle would be 10 plus 6, which is 16, and this side of the rectangle would be 10 minus 6, which is 4. So you see how the two sides of the rectangle are not equal. This is not a square, but it is a special pattern. So we have a name for it. This special pattern is called the difference of squares. So the difference of squares pattern, I want to break down the parts of this title. First off, let's talk about what we mean by squares. So squares are numbers that when we take the square root, we get a whole number. So for example, 36, if I take the square root of 36, I get 6 because 6 times 6 makes 36. And technically, x squared is also a perfect square, because if I took the square root of x squared, I would get x, because x times x makes x squared. So these are both perfect squares, x squared and 36. If we look at each of these different problems, you see this, we have a squared, x squared, that's a perfect square, and 49, that's 7 times 7. 4x squared is 2x times 2x, so that works, and 5 times 5 makes 25. 9x squared is 3x times 3x, and 1 is 1 times 1. So every number I've circled on here is considered to be a square. It's a perfect square. And then when it says difference, what this means is we're finding how far apart they are. We're taking the difference, we're subtracting the two squares, and look between every single one, minus, 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 minus. So this is where the title comes from. It's a difference of squares. So that's why we call it this. And then the way that the numbers in the original expression relate to the answer is also pretty special. So you know how I talked about the square roots of x squared and 36 in this first problem? So if I thought about this x here, the square root of x squared is x, the square root of 36 is 6. Notice how the notice how the factors are made up of x's and 6's. Just one is plus and one is minus. See in the next one, the square root of x squared is x, the square root of 49 is 7, and look at my answer, it's x's and 7's, one's plus, one's minus. And the same thing happens on each of these. The square root of 4x squared is 2x, the square root of 25 is 5, and look, my answers are 2x's and 5's. Here we have a 3x as a square root and a 1, and look, 3x's and 1's. So this is one of those like useful patterns that saves us a whole bunch of extra work if we can identify it when we see it. All right, so I'm going to go ahead and clear, and we're going to do a little bit of overview of each of these patterns, and then we're going to do a little practice. So this is back to the perfect square trinomial pattern, and I know it looks like a lot of things sort of floating around here. So I'm going to point out, how to sort of understand this set of details, this formula. So first off, take a look at, we'll just concentrate on the very first line here. X squared plus A squared plus 2AB plus B squared equals A plus B times A plus B, which is A plus B squared. So let's look at how the numbers relate. So notice how we have our first term here, A squared, and our last term here, B squared. And if we thought about the square root of each of those, A and B, that's what shows up here and here. The other piece that we need to be careful of is that middle term. So there is an important middle term pattern that we need to look for. So what has to happen is when we find this A, this square root here of A squared, so that's A, and the square root of this, which is B, the middle term is when we multiply those two together and then double it. Okay, so let's look at this in terms of actual numbers in an example. So in this first example below, do you see how we have x squared here? The square root of that is x. We have 36 here. The square root of that is 6. And then if we were to multiply those together, we would get 6 times x, and then we would have to double that to get the middle term. Do you see how 2 times 6x would make the middle term? So this is like sort of how to tell that the pattern is happening. And then your answer is just the square root of the first and last terms together in your squared factor. So see, check this out. 9x squared, the square root of that is 3x. 4, the square root of that is 2. Look at what's in our answer, 3x and 2. The only thing that is left to pay close attention to in this one is that the second term is negative, which means that the answer needs to have a negative. Okay, so just pointing out these details here, and we will get a chance to practice this. It'll feel better, I think, the more we do it. But you'll have this to always refer to. Okay. Now on the next slide, the difference of squares pattern is really more, I think it's just like a little bit easier to see because there's less to keep track of. We have a perfect square minus another perfect square. If we take the square root of the first one and the square root of the second one, then we just use those A plus B and A minus B in our factors. So you can see in these examples down here, 9x squared, the square root of that is 3x. 16, the square root of that is 4. And look at our answers, 3x plus 4, 3x minus 4. Done. Okay. Works here too. The square root of 4x squared is 2x, because 2x times 2x makes 4x squared. The square root of 81y squared is 9y. And then look, 2x plus 9y, 2x minus 9y. So that's like a nice sort of fast, we get to skip all the hard work in between when we see this pattern. Okay. All right, so let's do some practice. So first off, they're asking us to identify, are any of these perfect square trinomials or any of these difference of square patterns, excuse me. And then if we can, let's factor them. Okay, so for the perfect square trinomials, let's call these perfect square. Does anyone have any thoughts on which ones might be a perfect square? A perfect square trinomial. Is A a perfect square trinomial? It's not even a trinomial, it only has two terms, so no. How about B? Let's test it. Does it fit the pattern? Let's check the pattern. Okay, we have an x squared, we have a 36, so that's like a good start. Square root of this is x, square root of this is 6. But does the middle term, sorry about that mess, does the middle term look like x times 6 doubled? No, 6x doubled is 12, and the middle term here is 5. So that's not one. So that's not a perfect square. How about C? Is C a perfect square? Maybe. Let's test it. So we've got x squared here. Let's get that root. That's x. We've got 16 here. The root of 16 is 4. If I do 4 times x and then double it, do I get the middle term? Yes. This is a perfect square. So we're going to follow our pattern here to do this factoring. So we have, since it's a perfect square, we know our answer is our factor squared. We take that first factor, which was x, like the square root of x squared. We take the last one, which is 4. The middle term is positive, so guess what? Our answer has a plus, and we're done. We don't have to do any extra area models or other business. That's it. Okay. Are there any more that fit the perfect square pattern? Any ideas? I'll throw it in the chat. Do you think that D does it? Let's test. Okay, we've got 9x squared. Let's see, the square root of that is 3x. We've got 4 at the end. The square root of that is 2. If we multiply those together, we get 6x. And if we double that, do we get 12? Yeah, we get a negative 12, but we'll work that out at the end. So this works. This is the perfect square. All right. So we're going to go ahead and remember our answer is a square. And then we take our first factor, 3x, and our last factor, 2. And then the middle term is negative, so that means we're going to have a minus in it. Okay, that's it for perfect square trinomials, since the other two ones are definitely not trinomials. Now let's look for difference of squares. So I'm going to call this DS. So check part A. So I have a perfect square here. 25x squared has a square root of 5x. I have a perfect square here, which is 1 times 1 is 1. So the square root of that is 1. And there's a minus in between. So this is a difference of squares. Difference of squares. Absolutely. And now we can factor without doing any extra difficult work here. We use 5x and 1 in both factors, and then 1's plus and 1's minus. And then part B is a trinomial, so that doesn't fit that pattern. Part E is a binomial, and it has perfect squares. But the problem with part E is that it's a sum. So that's not a difference of squares. But in part F, it looks like we have it. So we have 9x squared, we have 100. The square root of 9x squared is 3x. The square root of 100 is 10. And there's subtraction between. So we've got it here. This is a difference of squares, and our two factors will use 3x and 10. 1's plus, 1's minus. All right, so go ahead and finish up getting your notes down. I'm going to erase it in like 5 seconds. Hopefully this feels okay. Okay, so, all right, so here on this slide is a chance for you to practice the two patterns. So number 1 and number 2, I want you to just go ahead and dive in and try to practice these two patterns. Number 1 and number 2 are difference of squares, excuse me. And they do fit the pattern, okay? And then down here, number 3 and 4 are perfect square trinomials. Okay. So yeah, just take a few minutes and see if you're able to do these on your own. So I'm looking at your work right now to like monitor to see where you're at with this. And if you have any clarifying questions that you want to ask in the chat, go ahead and do it. Okay, and these are not yes or no questions. These are, you have to factor them. All 4 of them factor using one of the two patterns. So the first 2 factor using the difference of squares pattern, the second 2 factor using the perfect square trinomials pattern. And there's no tricky business here. They all work in their pattern. So the idea here is you don't even need to use the area model anymore. You can just do the shortcut. You can always go back to the area model if you want to, but I want to try to urge you to try the shortcut right now. It's just so much less work. So much less work. All right, and then here's kind of a nice, like, sort of helpful thing. Remember, with difference of squares, your 2 factors in the end will be different. They won't be identical to each other. But with perfect squares, your factor will be squared. So this is what we're going for in terms of structure. So now it's just about what fits in, what goes in there. So I'm gonna give you another minute. So if you haven't tried this on your own, I urge you to try. And if you make an error, that's okay. And I'm going to go through these real quickly so that you see it one more time. But if you don't try it yourself, then you're going to have a very hard time like figuring out where your misunderstanding really is. It's just like with anything. If you watch someone else do it a bunch, it doesn't mean that you'll be able to do it yourself. you know, like skateboarding. You watch someone do a bunch of cool tricks on a skateboard and you think you got the idea, it doesn't mean that you can go out there and just hop on a skateboard and do it without practicing. Like you have to do it yourself. Okay, it looks like most people are finished. So let's go ahead and just double check our answers. So in this first one, we take the square root of our first term. 16n squared is 4n times 4n. We take the square root of our second one. 9 is 3 times 3. And then this is how we fill in our factors, 4n and 3 on both of them. One's plus, one's minus, and we're done. So follow the same pattern for number 2. For number 3, perfect square trinomial, I take the square root of the first term, which is 4b, because 4b times 4b makes 16b squared. I take the square root of the last term, which is 5, because 5 times 5 makes 25. And then in here I put 4b and 5, and then I double check the sign from the middle term, which is negative, so I'm going to go ahead and put it. You can use that as a guide for number 4. So I give you about 20 more seconds to wrap it up on this slide, to try to follow those patterns one more time if you weren't able to before, and then the answers are on the next slide. So careful with the signs in the perfect square trinomials. If the second term is negative, your factor will have a negative. The second term is negative, your factor will have a negative. So they will both have a negative in this situation. Okay, I'm going to clear mine. Let's check our work on the next slide. All right, so double check your answers. Is this what you got for number 2 and number 4? All right, so those were the major learning goals for today. But remember the meme from the beginning? My face, you add one more thing. I do have one more thing I want to show you, unfortunately, and I'm so sorry for this. Let's cram in one last thing at the end here. But sometimes this cube factoring with sum or difference of cubes comes up. So I want you to have at least a little bit of experience with it. So the sum and difference of cubes. So this is a little different than squares. We're not looking at squares anymore. We're looking at cubes. So like the exponents are bigger. The exponents are 3s instead of 2s. So what we have here is a cubed number plus a cubed number, or a cubed number minus a cubed number. And just to be really clear, a cubed number is a number times itself 3 times. So like an example of a cubed number might be like, you know, 125. That's 5 cubed because it's 5 times 5 times 5. So if I took the cube root of 125, I would get 5. So that's just like a side note about cube roots, okay? A number to the third power is the number times itself 3 times instead of 2 times for a square. And this pattern looks a little chaotic, but it's always the same. So if you have a sum of 2 cubes, what you do is you take the cube root of the first one and the cube root of the second one. So like A and B without the exponents. And then you have first one plus second one, and then first one squared minus first one times second one plus second one squared. It's weird. So what I have is it's kind of hard to remember those details. So what I have is a video on the next slide that is of this like really funny other teacher who has a silly song that can help us remember it. All right, so it's just a 2-minute video, and then we'll do a quick example or two at the end, and then we're done, okay? Here is the video. That's a 1 minute 50-second video.
First one, second one, first one squared. First one times the second one squared. Use some soap. Don't be nasty. Use some soap. The first part is a binomial. The second part is a trinomial. Okay? So I teach my students a little song. Okay? And that tells them what goes in every position. Okay? So the song goes, first one, second one, first one squared. First one times the second one squared. Uh-huh. Make sure you use some soap. That's the whole thing. First one, second one, first one squared. First one times the second one squared. Use some soap. It's obnoxious. They don't like it. But here we are. Okay, so so when I say use some soap, you don't want to be dirty, you don't want to be nasty, you want to use some soap. So the S in soap stands for same. So the sign that you're going to put in this position is the same sign that you started off with. So if you started off with a plus, it's a plus. If you started off with a minus, it's a minus. Opposite, that's the O in soap. The O in soap stands for opposite. So the opposite sign of what you started with. So if it was the sum of two cubes, you're going to start with a negative. Oh, you're going to put a negative there. And then if it was the difference of two cubes, then you would put a plus there. And then the A and the P in soap stands for always positive. So no matter what, if you started with the sum of two cubes or the difference of two cubes, that last sign is always going to be positive, baby. So that's it. First one, second one, first one squared. First one times the second one squared. Use some soap. Same sign, opposite sign, always positive sign.
Okay. Okay, so I'm going to show you what she actually means. And but it actually is kind of catchy and it works when you're trying to do problems. So here we go. So we have two examples and then we're done. Okay, so here's our first example, part A. So we have our first term here and our second term here. This is a sum of cubes because it's adding. And we get our square roots, or our cube roots, excuse me, of each one. So the cube root of x cubed is x. And the cube root of 125 is 5. And now we set up our parentheses, a small set of parentheses and a big set of parentheses. The first one has 2 terms, the second one has 3 terms. That's why I make them a little like smaller and larger. All right, when we say first one, we mean x. And when we say second one, we mean 5. So first one, second one, first one squared. First one times the second one squared. 5 squared is 25. So that's how we get all our numbers. So let me say that again. First one, x. Second one, 5. First one squared, x squared. First one times the second one, that's 5x. Second one squared, 25. And then we need use some soap. So SOAP stands for same sign in the beginning. So because the problem was plus, we start with plus. Same means plus in this case. Opposite minus, always positive. Same, opposite, always positive. All right, let's try that again. So in part B, we have the first term and the second term. This is a subtraction problem now. The root of x cubed is x. The root of 27 is 3. Small parentheses, big parentheses. First one, second one, first one squared. First one times the second one, that's 3. 9 squared, 9. Here you go. And then use some soap. So notice in this one for SOAP, same means subtraction. Opposite means addition. Always positive means addition. And we're done. All right. Hopefully that wasn't too freaky. So this is it for today. On the next slide is your closure. So I'm hoping you take a moment and reflect on the big ideas from the perfect square trinomial and the difference of squares. Um, and then your homework is posted for you on the last slide. So I'm making this student paste now, and please email me or come to tutorial if you have any questions. Have a great day, everybody.